Good morning, everyone. Oops. Welcome, everyone, and thank you for joining us in today's session with Sharial Garemanyan, who will take us through some information and insight on how to efficiently electrify commercial building HVAC system with heat pumps. My name is Alice Wallet. I'm the customer experience specialist with CIT, but I'm filling in for Megan today, who is working with ISO. Um, I will be simply facilitating this session today. So before we get started, just a few things. The session is being recorded. Both the recording and presentation in PDF format will be available on the Save on Energy website in 1 to 2 weeks. You can visit Save on Energy /training and support, which I will share in the chat, to browse all of our past webinars and other resources like guides, fact sheets, fact sheets, sorry, and tools. Please, during the session, if you could remain muted, make sure that you are muted right now, just because sometimes we don't realize we join the meeting unmuted, but we can hear background noises which can interfere with the presentation, so just make sure that you are muted and that you remain muted during the session. But you can use the chat to ask questions, communicate, react. You can also use the react buttons at the top of the screen if you want to react, applaud, laugh. Or if you want to ask question, you can also use the hand raise hand function. We have also reserved a 15 minutes at the end of the presentation for a Q&A portion. I will be monitoring the chat throughout the presentation for any question you may have. I will decide if it's a good question to ask right away, or if it's better to keep it for the end. Also, if you prefer to simply ask your question out loud, you can raise your hand and wait to be called upon, and I will give you the mic when you do. So you can present yourself, and maybe you can mention the organization that you represent before you ask a question. And with that, I will let Sharia take over.
Thank you, Alice. Good afternoon, everyone, and welcome to this session. This is, ISO has many sessions scheduled actually for this topic of heat pumps. We already did one, electrification of the building heating with heat pumps for residential sector. So this is the second one, which is we are going to talk about the institutional facility, or let's say public sector, and then tomorrow we have another session for the commercial sector. So then how the heat pump is getting fitted with the commercial sector. Uh, as Alice said, yeah, please, at any time, if you have a question, just raise your hand, and then I will ask you that to bring your question to everyone, and then we can have a chat about it. That's fine, because we want to have an interactive sessions. So as Alice said, that my name is Shahriar Kahramanian, and I'm going to present these, today's slides that we prepared for the heat pumps of the public sector. So this is an overview of our today's agenda, or the topics basically that we want to cover. So we want to see that the heat pump technologies that are available, and then how these heat pumps actually fit with the offices, social housing, and school cases that we prepared for you, and then some comments and some notes if you are going to consider heat pumps for your facilities or for your projects. Actually, it's good to know these items, and then to have actually asking the contractor or whomever is doing the design for you, they show you that they consider all of these options actually. So let's begin with an overview of how in Ontario the building sector is doing. So in Ontario, basically almost 20% of energy consumption goes to the building actually. And then the building sector almost 20 has a 25% of the total GHG emission. So 1/4 of the GHG emission comes from the building sector actually in our province. And on electricity, 1/5 of electricity consumption is getting used by the building sector as well. So this is a very high level, information. This goes back to 2019, and then uh, I assume that it's going to be almost remain the same, maybe 1% above or minus, but it's going to be the same for the last year. On the other note of this one, let's look at the Canada emission reduction plan. Actually, this is the plan that published by the government of Canada, by the federal government, and basically it's a requirement under the Canadian Net Zero Emissions Accountability Act, which basically establishes the regular milestones for tracking Canada's progress in this field. Actually, so in 2022, actually, the emissions reduction plan was released. After that, the Environmental and Climate Change Canada, they actually uh, published the first progress report in 2023. This year, they are going to set the emission target for 2035, actually. So then Environment and Climate Change Canada, they are going actually to publish the target, which is going to be some kind of an interim target before the 2050 target that's going to be published this year. So let's go to the future. So 2050, the goal is that all across Canada, we reach the net zero emissions actually, and then we have a target for 2035, which is going to be somewhere in here actually. If we want to go backward, then in 2030, actually, there is a deadline to reduce the emissions by 40 to 45% below the 2005 levels, actually. So that's the goal of Government of Canada, actually. So by 2030, we almost go halfway actually to 2050, which this halfway is much easier than the second one actually. So because this is just electrifying and switching, it's possible, but the rest it becomes a challenge actually. And then if we look at the emissions reduction plan in 2029, uh, the plan for the 2035 actually emission reduction is going to be established, and then setting the target for 2040. So that's the plan that we have. And then the progress report will be another progress report will be published in 2027. And then in 2026, 2 years, almost 2 years from now, we need to achieve the interim objective to reduce the emissions by 20% actually. So 2026 also is another target for Government of Canada actually. So let's see that how we do with this regard actually. If we don't do anything, then this is the thing that is going to happen. If we don't do anything, then it's expected that our GHG emission across the Canada is going to be increased by almost 800 megatons of CO2 equivalent. So you see that if we don't do anything, if we don't have any of these policies, we are going to see an increase actually on the carbon emissions of entire country actually. But the good news is that now we have lots of policies, lots of legislations, lots of developments, similar to today's session as well, is that we're bringing attention uh, to everyone and to understand that yeah, we need to do something about these uh, GHG emissions that we have from Canada, and then try to bring it down to this net zero actually pass. That's the ultimate goal actually. And in here, you see that each of these items that we have, the legislation, for example, is going to save almost 500 megatons. Development is going to be 500, another one, and then some announcement that is coming. So basically, these are the opportunities and the measures that the government of Canada and the other governments and all the governments that we have in different jurisdictions, like a city of Toronto, for example, they try to bring and then they try to reduce our GHG emission and makes our emissions actually closer to the path that we have for becoming net zero actually. So let's go back to those numbers that we saw, but let's look at that. How is the energy consumption in each sector? So residential consumes almost 20%, and the commercial sector, which I believe that the public sector is also included in the commercial, is 30%. So 50% of energy, actually, the total demand for energy is actually consumed by the building sector, actually. So this is an interesting fact that we need to consider when we are designing or considering any new projects for our facilities, actually. The same thing for the GHG emissions. As you saw, 25% of the GHG emissions actually goes to the building sector, which is again including the residential and the commercial sector, actually. On the market for the heat pump, there are a couple of studies that have been done. This is a study that done by one of the manufacturers of the heat pumps, actually, and you see that they see almost an $11 billion per year efficiency spending, actually, and an increase actually in the heat pump, actually. Let's say we are this year right now, and they expect by 2028 in North America, actually, that we are going to have almost $11 billion in of worth of market for the heat pumps, actually. Canada has a role in this one, so Canada's market is almost less than half of these, billion dollar heat pump installation market, but it's getting there, actually. So that's the market that is coming to us, and we need to take advantages of this one, actually. This is another study done for just specifically Canada and also air source heat pump. Later on, I will introduce that what is the air source heat pump, actually. But again, the value for this market in 2022 actually was actually $1.5 billion, actually. So the market in Canada for heat pump was actually $1.5 billion in 2022. And also in 2023, we see actually almost a 7% increase in the annual market for the heat pump, actually. So it's, as you can see, this is a new technology. It's not a brand new technology. It existed, actually, but now it's coming to the North America and Canada and US. They are taking advantage of that one. Now let's look at why heat pumps are good. What are the benefits or advantages of the heat pump? The first and the most important one is the energy efficiency. What does the energy efficiency means? That it means that for every 1 kilowatt or kilowatt hour of energy or electricity that we put in to a heat pump, actually we can transfer at least two to three uh, times amount of heat that we wanted to do that one. Either that's a heat that we want to remove it, like today, from inside of our building to outside, or in a winter season we want to bring, the heat from outside to inside. So basically, this equipment, these heat pumps, they are energy efficient, and their energy efficiency, we measure it. We cannot measure it by just efficiency. We have some terms for that one, but those terms like a COP, or coefficient of performance, for a heat pump at least is 2 to 3, actually, which means that for every 1 unit of energy that we can put input to the system, we can move 2 to 3 times, actually, of the heat. The next advantage of the heat pumps, actually, is their versatility, actually. So this means that the heat pumps can provide both heating and cooling, and they offer a year-round comfort with a single system, actually, which basically they extract heat from the air or the ground or even the water, and make them, suitable for various climates, like the cold climates that we have in Canada, actually. The other benefit that, indirectly I touched it, is the environmental benefits, actually, because heat pumps, they produce fewer greenhouse gas emissions, actually, and thanks to the Ontario, power generation, that we have a green electricity actually available to us. So we need to take advantage of that one. And not using natural gas actually for heating. So it's better that we switch to electricity and using electricity based systems actually like a heat pumps. So then we will have environmental benefits for that. These heat pumps also they improve safety because the heat pumps they don't burn any fossil fuel actually on site, like a boiler or like a furnace. We don't need to burn any fossil fuel at sites actually, so this will reduce the risk of accidents such as gas leaks or carbon monoxide poisoning, and this makes the heat pumps actually much safer for our buildings and also the building occupants. The other advantages is improved comfort actually. So heat pumps, they provide a consistent heating and cooling throughout the building actually and maintaining a more stable indoor temperature compared to the traditional systems that may produce some fluctuations in the temperature. So the temperature goes down and then it starts, our systems starts and then it starts to fluctuate. The other benefit is the long lifespan that we have. So basically, when if we have a well-maintained heat pumps, actually, it can have longer lifespan than the traditional heating, ventilation, and air conditioning systems. And also, we need to consider that with fewer mechanical components and less wear and tear from the combustion process, the heat pumps actually offer more reliable performance for many years. The other benefit, which is really good actually, is zoned heating and cooling. I have a couple of examples for this one as well. So if at our facility at any time that we want one area, they want to have a heating and the other area they want to have a cooling, the heat pumps, they can provide such a system. So we can have a zoning system within our facilities. And then that's going to be another benefit of our heat pumps actually. So in other words, the heat pumps reduce the overall energy cost because they are more efficient, at least 2 to 3 times more efficient. They will reduce the greenhouse gas emissions. So again, the net zero paths, we want to contribute to that one, improve comfort for the occupant, and also the longer lifespan that which, the lower maintenance cost. That's the one that we have. So we talked about these, advantages, but there are some disadvantages. So it's better that it's to be fair actually and mention them. So these heat pumps, they can be noisy. So they have a fan, and on the condensing unit, the fan is running, similar to air conditioning systems. So that can be noisy. So then we need to take care of that one, and we need to design a special place for that one actually. Uh, a low temperature supply limits. So there are some supply limit temperature actually for the heat pump. So when we design a heat pump, so when we size a heat pump for a facility, we need to consider that one. If we have a low temperature, which means that it's super cold outside, so the output of these heat pumps, they will be reduced actually. But again, they are not going to be much less than actually one. So their efficiency at least gonna be almost near one. And then for the retrofit scenarios, they can be highly variable actually. And then the electrical services that is available, also we need to consider that one because now we want to switch, imagine from a large boiler to a heat pump system. So then we need electrical system available or a large amount of maybe demand to our facility. Now let's look at what is a heat pump actually. So a heat pump is from coming from its name actually. A heat pump is a device, it's a mechanical device which moves the heat. Either it moves the heat in this direction actually, which will be, let's say, in a heating season, or it can be in moving in this direction, which going to be, for example, in a cooling season. So in a basic word, it's a mechanical system that it can move the heat for us from the places that we wanted to the next one actually. So this slide shows actually two cycles that the heat pumps they can operate on both of those cycles actually. So on the left hand side we have the cooling cycle of the heat pumps, and basically what we have a condensing unit outside which is similar to the air conditioning system that these days that in a warm weather that we are right now we are using. So the condensing unit actually, it takes the heat from indoor, from inside. This is inside our facilities. So basically heat is moving in this direction actually in a cooling season. So what you can see in the heat pump actually, so there are some components that we have. One of the big and the most important components is the compressor. So this is the compressor which compresses the refrigerant that exists within this cycle of the heat pumps actually. Then we have an indoor coil and an outdoor coil actually. What we have, which is really good, we and is different than our air conditioning system, is the reversing valve. So we have a reversing valve. Uh, some people they call it three-way valve as well. This reversing valve actually is doing the magic for us, and it actually can switch from the cooling to the heating. So if we reverse this reversing valve for heating season, which is going to be our winter, now what will happen is that now we move the heat actually from outside and we bring it to indoor of the buildings that we have actually. The components, everything remains the same, the refrigerant, the outdoor unit, the indoor unit, just the task of outdoor unit is going to be different and the task of the indoor coil is going to be different actually. So that's the basic um, information about this heat pump cycle, or if we talk about the engineering work, this is a refrigeration cycle actually. So now if we want to select a heat pump, we need to consider all these items that we have step by step and then moving up the stairs basically actually. The first and the most important one is that in the outdoor unit actually, what we want to take from the where we want to take the heat actually. The air source heat pumps, it's from name. That's the air source, means that the heat either is going to be dumped in a summer season or the heat that is going to be extracted in a winter season, it's going to be air one from air actually. So this is the most common, heat pump that exists in the market, but we can go and have a ground source heat pump as well, which means that the ground we put our refrigerant actually under the ground. And I worked on many projects across the Ontario, especially for GTA area, that the ground temperature all year around is between 8 to 10 degrees Celsius, actually. So no matter what we have outside, the inside or under the ground actually the temperature is 8 to 10 degrees Celsius. So depending on the season we can use the heat pumps actually, and then we can use that outdoor heat source that we have under the ground actually. So this is the first one that we need to decide. Yeah, the ground source heat pumps actually they are much more efficient. But in terms of the cost of it, so we need to drill the boreholes and then we need to put the refrigerant pipes in down there. And then, so down the road, the operational cost might be less compared to the air source heat pump. But, and also it's not going to depend on the outdoor air. So when my outdoor air is minus 25 degrees Celsius, it's super cold. Now, either we have to use a supplemental heat for our heat pumps actually, and then if we run our heat pumps, then we might have a difference that later on I will touch on that one. So that's one of the drawbacks of the air source heat pump, but they are, commonly available, and it's just in one machine that we go and purchase it for a facility. We can design it, size it, and put it there actually.
Sharia,
So this, yes, yeah,
we have a question if you want
sure,
to take a moment.
sure, absolutely.
Um, do you want me to read it out or do you want to read it yourself? I can read
Yeah,
it
you
out.
can read it. Yeah, please read it. That's okay. Yeah.
So, Lindsay asked, I have heard some people say that air source heat pumps will have shorter lifespan, higher maintenance than some conventional systems like electric or condensing gas furnaces. The rationale being that HPs operating in cold climates will heat pumps, sorry, operating in cold climates will experience relatively severe conditions that compressors in particular will experience more substantial wear than traditional AC and therefore a shorter lifespan. What are your thoughts on this perspective?
Uh, I would say that That is true, and also we can also have some solutions for that one as well. So uh, I agree that, I mean, if we are talking about GTA, we have a milder winters compared to the northern part of the Ontario, which the temperature can go lower than that one. But technology advanced a lot in this regard actually, and I would say that the cold climate air source heat pumps actually CCASHPs, they are actually they are very well designed, and their performance is much better actually. So these days we don't have those things on the cold climates, and on the wear and tear on the compressor we should consider some design considerations. So these are not like air conditioning system that if we have in our houses, we just cover them during the winter. But for the air source heat pumps, actually we need to have some sort of a shelter around it. If you're talking, I worked in a facility actually in the northwestern north of Thunder Bay actually, and we put the heat pumps inside the mechanical room, which was in the penthouse actually, and it worked perfect actually. And then it reduced the maintenance cost because it was indoor, it was inside, so the snow, the defrosting, and those kind of things actually didn't impact. So I would say that there are solutions and there are considerations that we can overcome this one. But again, it's not that efficient. If you look at the lifespan of these systems, they are much more efficient. Just think of the temperature difference that these systems they are working compared to the gas furnaces or the other boilers that we have. So they need to increase the temperature of the combustion, uh, you know, over 100 degree maybe Celsius to do the combustion, and then all those systems inside those heating systems that we have. So I would say that technology actually came to help us in this regard these days, and I don't think that we have a, a lower or shorter lifespan for the heat pumps actually. I hope that I answered your question. Okay, so let's go back to our uh, discussion. So we talked about that we need to decide that where where is our sink or source of the heat in outside or outdoor unit that we want to have it. Either is it air or is it ground. I didn't add the water, but the water is also good actually to consider if there are some water sources available to us. Maybe that's another source of the heat that we can use for outdoor unit that we have actually. The water one actually is popular in US rather than Canada. The next item that we need to consider is the indoor distribution system. So in our indoor distribution system, if it's an existing building, we have it. Either is the air, so we have ducted the air actually, and then we heat up the air during the winter season, and then we bring it to every space that we want. Or no, we actually heat up the water, for example, by boiler, and we bring the hot water pipes, and then we put the fan coils, and then use that one. Or the new systems is a refrigerant actually. So I will talk about the refrigerant as well. So you will see that one as well. So we need, if it's a brand new building, it's better that we think of the indoor distribution system as well. And as you know, the air has a lower heat capacity compared to the water, and water is also has lower heat capacity compared to the refrigerant. I mean, water and air actually, water is 4 times better than air actually, if we want to distribute heating or cooling systems actually that we have. And for the conductivity of air and water is the same thing. Water has 25 times more heat conductivity compared to air. And refrigerant is much better than these two as well. So again, if it's a brand new facility, or if we want to do a major uh, renovation in our facility, so then it's better that to consider these ones as well. And then in terms of space that we want for our distribution, again, refrigerants, they need a very tiny pipes actually. Waters, they need a little bit of larger pipes. And air, you need to have, considering actually a large ducts actually to move the hot air or the cold air actually. So that's the second consideration that we need to have for our heat pump selection. Then we go to the sizing of our heat pump for the heating and the cooling load. So I will chat about this one later on, but the heat pumps that we have depends on the price that we want and depends on their efficiency. There are times that we need to consider supplementary heat sources as well for our heat pumps. So because the heat pumps, they are designed to work up to a certain outdoor temperature, and after that, it's better that we switch to a supplementary heat sources actually. When we do the sizing, now we need to consider the efficiency of the heat pumps as well. But efficiency is actually uh, connected uh, or associated with the cost of the equipment that we want. So these are the terminologies that later on I will define them. What coefficient of performance, energy efficiency ratio, or heating seasonal performance, or the seasonal, energy efficiency ratio. So these are the terminologies that we need to ask our contractor or whomever is doing the design and see that, okay, what is the best equipment that available to us. If we go with the air heat pump that I told you, then the system during a certain times needs to defrost because the ice and the water gets accumulated on the condensing unit or outdoor unit that we have actually, and the system actually turns on, and then it does not do any heating or cooling. Basically, it's trying to defrost and remove actually the frost that exists. And these defrosting systems is available, for example, inside of our freezers and fridges these days as well. The heat pumps, they need to do the same thing. So then they clear up their heat exchangers basically. So then the heat exchanger can continue to work in an efficient way actually. Then installation is really important. As I said in that example, if we have a mechanical room which is enclosed and it's in a, for example, penthouse, maybe it's a good idea to install the heat pump there. So again, the installation and the location that we want to install the heat pump is also needs to be designed specifically for the heat pump. And then we need to consider the maintenance of the heat pump as well. What are the maintenance requirements that is coming from the manufacturers actually.
We have another question, Charia,
Sure. Yes.
from Kier, who's asking, would you consider a gas absorption heat pump for Ontario specifically?
Uh, yes and no. It depends that, the absorption system, they are good if we have heating and cooling, load at the same time actually. So then we can use those systems in a, for example, manufacturing plants or in a hospitals. That makes sense actually. So if we have both heating and cooling demand or we have access to the low quality heating, then absorption systems actually they are worth to consider and look at the design of it and then go for that one for sure. That's it, but it depends on the situation that we have actually. Okay, let's continue. So we discussed about this, the selection, consideration, and what are those items that we need to have it. Now let's look at the common heat pump systems that we have it in the market these days. So we have a single split system, we have a multi-split system, and then we have a package, rooftop terminal units actually, which this is a very important one these days actually, because when we buy an RTU these days, we can ask that, yeah, can I have the RTU that includes a heat pump in it actually? That's a perfect think actually, because they need to just add that reversing valve to their system, and then that's it. You can get basically a rooftop unit that it has a heat pump in it actually. The advanced, another advanced level of the heat pumps for the public sector that we can consider is a variable refrigerant flow and a hybrid heat pump system, which is going to be a mix of these systems that we are going to discuss actually. So the single split, they are very common. I mean, in an IT room in your facilities, maybe you saw that they just put their in elevator rooms actually, maybe you saw that they put there actually, or you have some offices or some areas that they require special cooling. So we go and we buy one of these outdoor unit, and then we run the refrigerant actually, and we connect it to an indoor unit actually, and then basically small institutional buildings, they prefer this one because it's affordable and it's suitable for their facilities actually. So this is good for small spaces, and because it has only one cooling unit like this, or heating unit actually, and then the fan and everything else is inside of this system actually. Similar to that one, we can go and have a multi-split systems basically. So they take less outdoor space actually, and it's good for better management of the indoor units as well. So the indoor units can be different units, either similar to the single split, or it can have some kind of a chill beams or anything else that connected to the roof actually. So this is another heat pump system that we can have it, or we can go and have a package terminal heat pumps. So this is a common, maybe in the schools actually, or school classrooms I would say, or some like housing system that maybe we have, community housing that we have. We just basically buy one of these units actually, and just cut the wall and then connect it to the outdoor, and then that's it. Everything is going to be inside this package terminal unit, which is going to be a heat pump during the winter season. It provides heating during the summer season, actually provide cooling actually. So this is also good for buildings that like community housing, that we don't want to run any docs, we don't want to run anything else, just we buy this unit and then that's it, we just install it actually. The uh, the rooftop unit, I touched on this one. So the rooftop units, they are used in variety of building types actually, and it's the most commonly used system for heating and cooling and providing the air actually. So these ones, they go to the roof of the building, and they provide heating and cooling and ventilation to the building actually. So these rooftop units can be like these, let's say in these two-story building. So basically direct ducting that we can have, and then all the mechanical unit, which is providing heating, cooling, and return and exhaust, and outside, air control, humidification. Everything is done by these rooftop units. These rooftop units, that they can become larger. So means that now we need to have an air handling unit, and this air handling unit is connected to an air source heat pumps basically actually, and then providing the same thing. And again, they have a size, different sizes, and they can work under the constant air volume system, or they can provide a variable air volume systems actually. So in here, in this slide, we have a constant air volume actually, which is providing a constant CFM of the airflow to the area under. So basically, the return air is coming from here, the outdoor air is coming here, and then the air is getting filtered, and then it goes to the supply fan, and then we have these the coil basically, which is doing the heat pump role actually for us, and then bring it down actually to bringing the air that we want, either is a cold air during the summer season or a warm air during the winter season actually. And this is typically good for the single zone units actually, but we can duct it to different zones as well. But again, this is a rooftop units that we can have. The other system is variable refrigerant flow heat pumps actually. So these variable refrigerant flow heat pump, basically it works instead of running the hot water or the chilled water, or we run the air ducts actually, we take the refrigerant to every space that we wanted actually. And basically we have the outdoor unit of the heat pump actually, and the outdoor unit is doing their job depending on the season and on the demand actually. And basically they either cool down the refrigerant and send it for cooling the entire facility, or they heat up actually, and then they take the heat from outside and then bring it inside of the building actually. So this is nowadays a popular technology for decarbonization of the heating and cooling because this is the most efficient HVAC system that we can have. So it has a low carbon footprint actually, and that's good for electrification, and it reduces the overall cost of the building owners actually. Another good thing is that these VRF heat pump system, we can use it either for the single zone application or multi-zone applications. And then the multi-zone application means that they can actually heat up at the same time that they cool down actually. So I have one example in the next slide. But before that, I mean, there are many studies about the variable refrigerant flow heat pumps actually, or VRF heat pumps, and they show a large amount of GHG emissions that you see. And also the fossil fuel for sure. When we switch to variable refrigerant flow heat pumps, almost 60 to 80%, we are going to reduce the fossil fuel need actually, and also around 30 to 40% actual reduction in our GHG emission depending on the existing system that we have actually. We have two types of VRF heat pumps, I would say. Typically, we have a VRF heat pumps, which they are on the top pictures that you see here. So basically, we have an outdoor unit, and this outdoor unit actually provide heating to zone 2 and zone 3, for example. And then another outdoor unit, number 1, provides cooling. So basically, unit 2 and unit 3, which they are connected to one single outdoor unit, they have to follow each other. So they cannot, one of them, unit 2 says that I want to run heating, and the unit 3 says that I want to run cooling. That is not possible actually. If we want to give that independency, then we need to have a 3 different outdoor unit basically for the heat pump, and then they can decide what they wanted. The hospital is a good example of these kind of application. Schools is another one actually, because some areas of the schools maybe they get heat up, so they need to cool down actually. So then but outside is a winter season, so that's a good one to consider. But technology is actually here to save us, and there are VRF. It's called VRF heat recovery heat pumps, and basically they have a 3-port branch controller box, which means that we are going to have only one outdoor unit, and this outdoor unit connected to this branch controller box, and depending on the load of each area, it can provide heating and cooling actually at the same time. So that's the beauty of a VRF compared to the heat pump actually. I talked about this one, but I wanted to have it again here. It's better if we are doing a new facility, it's better to consider a hydronic system or variable refrigerant flow systems actually, because they are much, much more efficient than the air-based system, because air has a less, heat capacity in it actually compared to the water and to the refrigerant. And the systems are running. Most of the European countries, they actually have a hydronic heat pumps in their facilities actually. Now, let's compare all those systems that we talked about it. Let's compare one by one and see that, what are the advantages or, disadvantages of each of them compared to each other. So if we talk about the single mini split, this is the only single connection, which means that we have one indoor unit connected to one outdoor unit. And this is just good for one space, actually. This is good for one individual room or zone that we have. And then that's it. One thing that we need to consider is that this system either can heat or can cool. That's it. So the good thing is that compared to the existing system, for existing system, we need to have a separate heating system and a separate cooling system, like air conditioning and a furnace or a boiler. But a heat pump is just one unit and it's good. But again, it has a limitation on its size and on the load actually. The other one is the multi-split, which is can customize based on the temperature zone actually, and it takes less space, less outdoor space, because then we have an outdoor unit and then we run that one actually. So again, this is a good one to have it. And then we go to the rooftop unit. So rooftop unit can be centralized, and it's suitable actually for medium to large commercial spaces, similar to the public space that we are talking about. The the accessibility of the roof actually simplifies the maintenance and repairs as well. So that's another consideration that we have for the RTUs actually. The variable refrigerant flow, that's a good thing. They can provide simultaneously heating and cooling actually, and they can be adjusted to the actual heating and cooling need for different zones. So maybe we have in our schools, we have a gym, and inside the gym, the kids are, playing, and there are some people are watching. So now maybe there is a need for extra cooling. So then that can be provided by the VRF actually without impacting the rest of the facility actually. And then it has the highest efficiency system compared to other source of heating and cooling. And then we can mix up. We can make a hybrid, heat pumps actually, and combine it with the existing system and adding some kind of auxiliary systems to the one as well. Some parameters also that we need to work on actually. So when we switch from the existing system to the heat pump actually, so typically the indoor coil needs to become larger because the heat pump is operating on a different system actually. On the same note, the indoor air volume, the amount of air that we need to supply needs to become larger. So for example, if we were providing 1000 CFM, now maybe we need to provide 1800 CFM actually. So that's the difference because we are switching to a heat pump actually. And then inside our building, we have an air movement or air distribution system. One thing that we need to consider is a flood bag. Flood bag is when the refrigerant coming back to the compressor and then, can damage the compressor actually. So we need to be careful. But again, these days, the technology this is available from the manufacturer. This doesn't happen any so often actually. And the frost controls as well for during the heating cycle. So again, this is a control inside. And if we see that, yeah, there is no heating coming to the building, but our heat pump is working, that's the time that the system is actually doing the defrost. And the most important one is a supplemental heat may be required, depending on the climate zone that we are and depending on the sizing of the heat pump and its efficiency, then we might need to consider supplemental heat, which means that when outdoor temperature becomes lower than certain temperature, so we need to shut down our heat pump system and then use basically the supplemental heat that we have. Actually, 90.1 and other standards that later on I will show you, they have, efficiency regulations, and every 2 to 3 years they publish actually, and they say that, yeah, you need to consider these, efficiency for your systems. For example, for a single package vertical heat pump, they say that the COP greater than 3.3, for example, and depending on the sizes. So if the size is less than 19 kilowatt, that's the COP that they recommend actually, or that's a minimum efficiency. So if you are going to purchase that, we need to consider. If we are going to install a larger heat pumps, again, let's say less than 70 kilowatt, for the cooling capacity, for example, the COP should be greater than 2, and so on. And then if you have a single phase, single package central heat pumps, again, the we have the heating seasonal performance efficiency greater than 5. And you can refer to the ASHRAE 90.1 or other ASHRAE standards to find out what is the most recent minimum efficiency requirements for the heat pumps actually. Before doing these things, I want to again one more time review the energy hierarchy that heat pumps actually is here. So this is the discussion that we have today here, which is going to be the heat pump. But first of all, that if we are going to do any kind of thing related to energy and carbon reduction, actually, we need to do the study first. So without doing a study, we shouldn't do anything. So we should study the whole facility and doing an energy audit and analyze the whole system. And then we do next step is that actually, so the next step is that doing the energy conservation. So turning off the lighting that we don't need, turning off the heating system that we don't need, or cooling system that we don't need, like a setback during the nighttime. That's an example of energy conservation. After that, the next step is actually to recover the waste energy. So this is an actual system that I saw in one of our the public facilities, that all the exhaust air actually that is going to be getting outside of the building, they put a heat pump, heat recovery system. So this is an interesting thing, a heat recovery heat pump system. So all the air that is going out is going through the heat pump, and basically similar to that absorption that our friend asked actually. So it tries to extract the heat and then bring it back to the facility. So recovering and reusing the waste energy, that's another uh, step that we need to consider. Now it's if we if we did all of these three steps, now it's time to consider improving our systems. So considering a high efficient systems like the heat pumps, that's the time now to do that one. Or adding insulation to our facilities or switching to LEDs. These are all improvement the efficiency of our system. After that, we need to do switching to renewable energy, which after 2035, actually, I would say that's going to be the time that we need to consider. And in those times, we need to now consider, because now we did all of the first four steps of in energy hierarchy. Now we need to bring, a more greener, I would say, electricity to our facility. If we did all of those first five things, now we need to offset and then use the conventional systems actually. So let's look at there are lots of surveys about the heat pumps outside. We touched on some of these ones, for example, energy efficiency. There was a government incentive, but now there is no, just for the low income, and then those ones that they use oil for heating actually. But on a long run, it's cost saving to use the heat pumps actually, and it makes energy independent, and it's a long term investment, and it's also reduced maintenance, and also it increased the asset value as well. On top of all of them, it's going to reduce the GHG emission from our heating system. But at the same time, the barriers that the building owners, they talked about it. The initial cost is higher. Yes, the investment cost might be higher, but if we look at the whole life cycle cost, then we'll see that the heat pump becoming the winner of that one actually. The other reason is that I mean, the contractor and some people, they don't have enough information about the heat pumps. So the lack of awareness or the perceived reliability issues, again, these are the rumors that going into the market, which is not true actually. Some people, they refer to the technical challenges. Again, that this is not a new technology, but we need to have a technicians and the people that they are able, to work with these systems and repair them, to maintain them, and so on actually. The heat pump required in a special space. It's not easy that we put everywhere, so we need to consider that one. And access to the financing, which is again is related to the initial cost actually. And if there are incentives, if there is a possibility to get those ones. For the heat pump sizing, actually, I want to just touch a little bit on this one as well, which is for the heat pump, usually when they want to do the sizing, there is something it's called thermal balance point. In the next slide, I will explain it in more details, but the thermal balance point is the condition where the heating output of the heat pump becomes equal to the heat loss rate of our building. So our buildings, we lose heat during the winter season. Now, at which point our heat pump can supply that heat. Below that number, we need to provide the supplemented heat actually. And the heat means that the heat pump cannot provide heating to our facilities. So let's look at this building. So this blue line that you see here, it shows the heat loss through our building actually. So basically, and then on the horizontal axis that we have, this is a outdoor temperature. Means that when outside is minus 15 degrees Celsius, our building loses more heat actually. When the outside is, let's say, 18 degrees Celsius, basically, our building doesn't lose any heat. So this is a plot that shows the heat loss of our building, basically. The red line that you see that is crossing that, this comes from a heat pump manufacturer. And basically, the heat pump manufacturer says that, yeah, at minus 15, I can provide this much heating. And then let's say at this temperature, I can provide you this much heating, actually. Basically, this is the point, this is the balance point that we have. So it means that this area that we have on the left hand side of the balance point, this is the point that this is the time that we need to shut down our heat pump and then run basically a supplemental heat, whatever system that we have it here. For example, in here, what I calculate is that we need an auxiliary system of 10 or almost 11 kilowatts actually for this, specific situation that, we have in this example actually. So the balance point when you're talking to a designer or a contractor, so make sure that they provide you the balance point for your facility, and then design the heat pump system based on that, and then let you know that how much extra heat or how much auxiliary supplemental heat that you need to during the very cold days actually. But these days there are, as I said, cold climate air source heat pump. They call it CCASHP. These CCASHPs, they are designed to work up to minus 31 degrees Celsius, actually. And which means that we don't need actually any supplemental heat. And also adding to this global warming that is happening, just one more thing that to consider is that now we are going to require less heating and require more cooling actually. That's because of the global warming. From here, I want to introduce some of the term or terminologies that is related to the efficiency of a heat pump. The first one and the most important one is the coefficient of performance, or COP. Basically, COP tells us how much heat transferred by the heat pump, either is a demand kilowatt or is an energy kilowatt hour, divided by the amount of electricity that provided to the heat pump. In this example that I have, we see that 1 unit of electricity provided and 4 units of heat actually provided to us by the heat pump, for example. So each heat pump manufacturer, they have to report on their spec sheet or on their tag that how much is their COP. But as you see, COP depends on the outdoor weather as well, so it's changing. It's a variable, depends on the outdoor weather and depends on the set points that we have inside our facilities actually. But again, all the manufacturers, they have to report this one. The next performance terminology for the heat pumps is the energy efficiency ratio, or EER. This is just for the cooling capacity of the heat pump. Basically, it tells us if we move cooling actually, which means that we remove heat from inside of our building to outside, divided by the amount of electricity that provided, how much is that efficiency? So EER is just providing the cooling output or the cooling efficiency of a heat pump actually. And this is again in a steady state measurement at a fixed operation condition. And then there are standards by ASHRAE that the manufacturers, they have to meet those standards. And then, each of them, they will come back with an EER actually. So typically the above average EERs, they are above, let's say, 8.5 and higher than that. And then below average, the EERs are less than 8, I would say. Similar to EER, we have a heating seasonal performance factor, which is basically measuring the amount of heating provided by the heat pump divided by the amount of electricity that we put into our heat pump. Again, this shows this HSPF, shows the heat pump's heating efficiency over entire heating season, actually. So over entire season, it shows that how much, is the efficiency. So this is another metric that we can ask, or we can see. We need to look at the spec sheet coming from the manufacturer of the heat pump actually. The other one is the seasonal energy efficiency, or SEER. Basically, seasonal is again related to the cooling divided by the amount of electricity, and it covers other aspects. So it's the shoulder season and other ones as well. So there is a standard, but again, the best one, which is again more expensive, SEER of 20 and above that one, but the basic SEER is around 13 actually that we have. This slide, it shows actually the annual saving, let's say for just the cooling for different SER. So if we say that SER of 8, we don't save that much. But if we go to SER of 22, we are going to save the cost of electricity by almost 64%. So always look at the life cycle of the equipment that you are purchasing, or the heat pump that you are purchasing. Yes, maybe the initial cost of the heat pump with a CER of 22 is much higher, but it's better that we compare that one and then put it into life cycle analysis and see that, okay, how much is the total cost, which includes the initial cost plus the operational cost of a heat pump actually. So again, these are the trade-off that we need as a building owners, or the designers. We need to do that one between the performance and efficiency and comfort and the cost actually. So basically, the cost of the system, of purchasing the system, and cost of operating versus the quality that we get actually, versus the efficiency, performance, and the comfort that we get. So it's going to be a trade-off, and we need to manage that one again. In here, again, what I have is that actually comparing different heat pump COPs actually, and showing some sort of a relative efficiency. So basically, if we say that if we purchase a heat pump at a COP of 2, compare it to a heat pump with a COP of 4.4, that heat pump is almost 120% more efficient than the COP of 2 actually. So this is a this is another way that we can combine all those metrics, and we take a look at that one. So it's not just going, say that, yeah, if we go from 2 to COP of 4, but it becomes the COP of 4 is actually 100% more efficient than a heat pump of COP of 2 actually. This is just a list of codes and standards for the heat pumps. There are many of them and many new ones. So ASHRAE has many standards that have. So that's a good one that we refer to that one. Either we want to go for variable refrigerant flow, either we want to go for a single package vertical, air source heat pump, or other types. There are many standards that either published by CSA, by ASHRAE, by AHRI, or other organizations that we can refer to them and benefit from them once we are going to select a heat pump for our facilities. ASHRAE 15, for example, a standard 15, it has a design concept for a VRV, or VRV system, or variable refrigerant flow, or variable refrigerant volume. Actually, they are the same system. So ASHRAE 15 and ASHRAE 34, they have all the consideration in them that what we need to do when we go through design of these systems actually. So it's better to consult with these standards if we are going to choose VRF or VRV systems actually. Now let's look at some case studies and see that how these air source heat pumps is going to be used in different buildings. If we are talking about an office public sector building actually, so then depends on the size of the building. If we have a high-rise office building, so then typically the perimeter is a fan power VAV terminals, and then induction or a fan coil systems is getting installed. And for a small or medium-sized office buildings, air source heat pumps or mini split heat pumps, or even variable refrigerant flow can be a good, systems. Beside these ones, again, a package terminal heat pumps or a rooftop unit heat pumps, again, those are the good solutions for these type of office building again. But again, if we are going to consider uh, not a rooftop unit, or we don't have a, let's say we are going to use a VRF, then we need to bring the ventilation system by DOAS system, by using a dedicated outdoor air system actually, because in VRF, we don't run the air actually through the building, but basically we run the refrigerant throughout the building actually. So this is from ASHRAE HVAC applications, and depends on the system, on the basically on the size of the facility, and on if we want to have a centralized or a decentralized system, or if we are going to have it just maybe heating only. But again, a ground source heat pump, a hybrid ground source heat pump, or a package, single zone or variable volume units, or any commercial split system, a heat pump split system, or we go with a variable refrigerant flow. These are good solutions to be considered for an office facility actually. Another example is the transportation centers like a rail transit, bus terminal, airports, or similar to that. To those ones again, either we go with a decentralized system, which means that we can have a water source heat pumps or ground source heat pump, and then or light commercial split system or mini split, variable refrigerant flow. It can be a good option for these type of facilities actually. For the schools, we can have any of these systems. We can have, a rooftop unit, which typically the schools that they have with these, rooftop units actually. But again, temperature control becomes an issue when we go with the rooftop units, because you have only one unit, and this unit provides, heating or cooling, and it has a certain amount of, typically the rooftop units, they are constant air volume, so they just provide the constant air. So that becomes a problem. On the other hand, it's the chiller and boiler, which is, that's the idea, is that we want to switch from the boiler to a heat pump. That is possible actually. And if you want to do it, maybe variable refrigerant flow can be a good actually solution for this. So maybe that's a good idea to consider this one. But one thing that we need to consider, if we do a major retrofit, or if it's a new design, VRF is a perfect for solution for those situations, rather than existing system. If you want to just switch some equipment, maybe VRF is not a good solution. What are important factors for schools? The different level of occupancies. We have a classroom, we have a gym, we have an office area, assembly, and so on. So again, different occupancy levels, across the facility. That becomes a challenge when we do the design of the heat pump system. Different requirement for different spaces. Some spaces might require more heating or require humidification or dehumidification. Again, heat pump can be a good solution because of this. Then uh, some school they want to have a common system for the entire schools that they have within their jurisdiction. Again, that also can needs to be changed a little bit, so we need to consider heat pumps coming to the school boards. Limited funding and the life cycle cost needs to be studied for the schools then we have. And also the schools, another challenge is the limited construction schedules, because if the kids are at school, so we have a limited availability to do the construction or retrofit actually. So in here, as you can see that now we have a variable refrigerant flow, and then we have an outdoor unit, and then we have a controller. The good thing is that with this system, now we can heat up, let's say, these 4 zones actually, and then cool down the other 4 zones at the same time. This is possible using a ground source heat pump or a VRF hydronic system, or having a rooftop units that designed for each of these systems as well. So let's look at the pros and cons. If we are going to have a heat pump with a rooftop unit, so this is a easy to install for the existing rooftops actually, and it minimize the disruption to the schools. So that's a good one. It can provide both heating and cooling at this if we want it. And rooftop units are typically modular and can be expanded or replaced as needed, and they are cost effective compared to other systems that we have if we are going to consider the infrastructure. But the cons is that it requires regular maintenance and cleaning, and the efficiency can be affected by the conditions like shading or exposure to outdoor weather. And these rooftop units might not be as energy efficient as the other one actually. But VRF on the other side is high efficient, but it requires, higher initial investment as well, and it requires a professional installation and maintenance actually. And then again, it's a complex system compared to the other systems. But again, the good thing is that we talked about it. These systems, they can, have one outdoor unit and then connect the different systems to them, and then providing heating or cooling, and they can work up to certain temperature these days, actually minus 31 degrees Celsius. That's coming, this temperature coming from the manufacturers actually. If we are going to have a larger system in need, so then maybe air cooled or water cooled, heat pumps on the roof. That's going to be the unit that we need to have it actually for our facility. But if we go with a VRF system, then the outdoor air system, which is required for the ventilation of the building, is required because we just running the refrigerant for heating and cooling purposes. So now we need to bring outdoor air for the ventilations actually. Again, ASHRAE has numbers for the schools actually, so that's a good one, and different configuration like a parallel configuration or hybrid parallel configurations. Again, how to combine the units that we have with the outdoor unit. That's the possibility that we have with the VRF system, or we can have a ground source heat pump. This is a one school actually in US actually, so they installed the ground source heat pump in their front yard of the school, and now they're benefiting from that one. Yes, the installation cost was higher, but the life cycle cost, if you look at it, is much less than the conventional systems actually. Let's look at the community housing buildings. Actually, for community housing buildings, again, we can consider larger scale VRF or connected to vertical stack, or we can use, sorry, vertical stack heat pumps, or connected that to vertical stack fan coils actually. But again, the first cost, the utility cost, the available floor space and the temperature control, and how we want to do the tenant building, and how long we have for installation and the maintenance becomes very important. But again, we can have, the units on the roof, the units of condensing unit or the heat pumps on the unit on the roof, and then each, section of the building, they can have their own, fan coils basically, and then those fan coils inside, they might have, a system to bring the heat pump, and if it's required, we need to add the makeup air units to them as well. So again, this is a system now. We have an air-cooled VRF system or heat pump, which is on the roof. And then typically which unit, I mean, it depends on the units and, the levels. We can have, variable types of heat pumps actually connected to those ones actually. So as I said, this can be on the roof, which is going to be the water cool, or it can be connected to the ground, and then the ground basically does the cooling and heating source for us. So in here, this is a vertical stack that actually, heat pump or heat recovery that we have. These are typically 1 to 2 tons actually that we can have in each, community housing buildings. So it's good to have that one, and basically, this is the unit that we have, and then for corridors, we need to bring the make, some outdoor units. Actually, it might be a little bit noisy, but that's the units that we are going to design, and each unit they can decide what they want. Is it heating or cooling actually, and then we can have a metering for each tenant or each section of the building that we are talking about actually. These, vertical stack fan coils unit, they can have a larger or smaller sizes. These are the conventional systems that we have, which have a chiller or boiler, But instead of these ones, now we can have they turn off and they switch to one of them. We can switch to a heat pump and then use these heat pumps actually. So in this slide, you see that the different variable refrigerant flow versus a water source heat pump versus a fan coil or a package terminal AC. So we see that the efficiency of each of them, the package terminal AC usually has a lower efficiency and the comfort is medium versus the variable refrigerant flow, their comfort is higher and the water source heat pumps actually they have a medium to good, efficiency. But when you look at the cost of it, so it depends on the size of the project. Is it a small project or is a medium or large project? Again, it depends on if for a small project, maybe some of these systems becomes more expensive and it's not worth it to consider. But for the large projects, for sure, we need to consider these options like a VRF or water source heat pumps actually. Now, what factors impacting actually the rate of return or return on investment of the air source heat pump? So the cost of purchase and installation for sure, that's the first cost that we need to consider. The other one is that if there is any incentive available these days now, the SOFIAC that exists, for example, or Canada Infrastructure Bank for larger organizations like University of Toronto received that funding from the Canada Infrastructure Bank, and there are many other organizations they receive those kind of incentive. That's a good one to be considered actually. The cost of electricity is really important. The cost of electricity is increasing, and that's for sure. We cannot avoid it because now we need more electricity, and lots of our generation needs to be refurbished. So the cost of electricity becomes more expensive. But at the same time, the cost of natural gas is going higher. So the cost of increase of natural gas prices is much faster than the cost of increase of electricity actually. The fuel pricing and the carbon tax that exists, that is getting added to the cost of the natural gas that we have. The efficiency of the heat pumps that we talked about it is much more better than the conventional systems that we have, but we need to consider the size and the power output of the heat pumps and the local climate that we have again. So all of these, they impact on the return on investment of an air source heat pump, for example. For any air source heat pump, we need to consider. In the next few slides, I just want to go through some myths that exist and then showing the fact that those are not true actually. So they say that, yeah, the electric grid do not have the capacity for heat pump. That is not true. The electricity grid actually in Ontario, ISO, OPG, everyone is taking a look at that one. And then we have, good electricity and we have a green electricity in here. So it's better that to switch to an electrified heating system. They say that heat pumps is more expensive than fossil fuel based heating system. Yes, the initial cost, yes, this is true. But if you look at the lifespan cost of or life cycle cost of a heat pump, you will see that the heat pump becomes cheaper or less expensive actually. They say that Canada is too cold for heat pumps. That is not true. The technology, there is a proven technology from the big brands actually that they have a cold climate heat pumps that they can operate up to the temperature of minus 31 degrees Celsius actually. There is a myth they say that Canada would be alone if for requirements for cleaner and more efficient heating were introduced. It's not true. In Europe, Austria, France, Ireland, Netherlands, Norway, all of them, they banned actually oil and natural gas boiler systems actually. And any new buildings in those countries after 2023, they cannot install an oil burning or natural gas burning systems actually. New York State, the same thing. San Francisco, the same. So it's coming, and this is the Canada is not going to be alone actually. Another myth is that heat pumps are not climate friendly because of their refrigerant. No, that is not true actually. So most heat pumps in Canada currently they contain high global warming refrigerants emissions that they are much less than those ones that we think, and that the heat pump adoption is not going to impact that one because These are packaged by the manufacturers, and then they are not going to release to outside. Uh, there is another me saying that HVAC contractors do not support heat pumps. Yeah, actually, contractor associations, they support heat pumps, and they say that it's a better work, better customer experience, and better business opportunity. As you saw, the $11 billion, that's in the horizon for North America. Actually, they say that a gas furnace can still heat if there is an electric power outage, which is not true. We have lots of exhaust fans and some and other stuff connected to the gas furnace, basically, which means that without electricity, the gas furnace that we have cannot run. So that is not the independency that we are talking. For installation, it's the best practice to follow the manufacturer's recommendation. That's the most important one. So the spec sheet provided by the manufacturer needs to be studied by the designers and then design specific heat pump for the facility. All the local, provincial, and national codes needs to be met for these. ASHRAE has lots of good standards for this one as well. The equipment performance needs to be verified by the published product data that exists, and the job site needs to be ready for installation of the heat pump. As I said, heat pump is different than air conditioning and other systems, so we need a special place for the heat pumps actually. So a few tips, the factors that impact the feasibilities, the code and standard and regulations that we have. What are the existing heating and cooling systems? And then do we need a supplemental heat or not? If we need, what kind of supplemental heat that we need? And then electricity capacity at the panel and the feeder, because now if we need a larger, electricity demand because of the heat pump installation, so that should be also considered. And the financial support, that's another incentive that if it's available. So that was, the slides that we prepared for you, presenting the heat pumps applications to you. Any questions, anything, more than welcome.
So if anyone has any question, you can unmute yourself or you can ask them either in the Q&A or the chat. But I'm sure Sharia would love to converse with you. So if you want to come off mute and ask your questions, we still have 5 minutes. So it's a good opportunity if you have anything burning your mind.
Yeah, please unmute, as Alice said, yeah, unmute yourself and ask questions. Or if you're comfortable, you can just type in your questions, so then we can go through them.
I guess I was going to ask, is there any cases where a heat pump might not be the most efficient solution? Obviously, in very, very cold climate, but other than that, are there any other cases that we should consider as maybe not being, as heat pumps not being the best option?
The only reason is the affordability that I can refer. But technologically, I would say heat pumps is here and is more efficient. I mean, if you look at the basic engineering thermodynamic cycle, you see that heat pump is more efficient than the combustion, fuels. Let's say at the best boiler that we have is 84% or 90% efficient these days, actually. But a heat pump can deliver heat actually more than 100%, which means that so the only reason that I'm seeing that in the projects is the affordability or the initial cost of it actually. But at the same time, design needs to be done by the professionals because it depends on the facility, on the climate locations, and the energy hierarchy that I showed you. It's better that we go through all of them and we reduce the load that we have within the facility actually. But I haven't seen any applications that the heat pump cannot be installed actually.